We are we are a branch of, we are a chapter of the National Space Society. We started back in the 1970s, based on the work of Gerald K. O'Neill, who came up with the idea of creating large kilometer-wide space colonies in the Lagrange points. That's why we call ourselves have the L5 in our name. Later on, we were combined with the National Space Society. And tonight, our guest is Dr. Eric Lerner. He is the lead scientist for LPPFusion, a group that is currently working on developing a commercially viable form of fusion that involves hydrogen and boron 11, which is supposed to be aneutronic and does not produce any neutrons. Also, he is the author of the book, The Big Bang Never Happened. All right. Okay, you can go.
Okay.
Let me make you host real quick. You should have it.
Okay, can everybody hear me?
We can.
Yes.
Okay. So let me share the screen here. Just a second. Sorry, I'm having a little difficulty here. Just a second. Okay. Okay, can people see this?
Yes.
Can people see best yet measurements deepen cosmological crisis?
Yes.
Okay.
You still have all the slides on the left side, so you might want to put it in presentation mode.
The problem, I think, with presentation mode is that it freezes on the first slide.
Okay.
So I think we can just take it from here. This way I know that you'll be seeing the same slides that I am. So thanks for the invitation. And this is also a meetup of the New York Physics and Astronomy meetup group and the Clean Energy group. So welcome to all. So clearly, if anybody has been following this field at all, they're aware of that there is a crisis in cosmology. And this has been reported over the past 2 years in a number of different publications. It's not advancing on my screen either, just a second. This worked before. There we go. And as the introduction sort of gave away, the question is, what is the cause of the crisis in cosmology? And in the first part of this presentation, I'm going to be presenting the reasons why this crisis is being caused by a failure of the basic paradigm of current cosmology, which is the Big Bang hypothesis. The only way out of this crisis is to recognize, as I wrote 30 years ago, that the Big Bang never happened. So after this first part of the presentation, we'll have a brief break for questions, and then we'll go on to the second and third parts of the presentation, where I'm going to be presenting, if the Big Bang never happened, what did happen in cosmic evolution? And finally, what difference does it make? And especially, what difference does it make to the effort to develop fusion energy? And then we'll have a longer period of question and answer. So to begin with, the problems of the Big Bang hypothesis go way beyond what is generally discussed as the crisis in cosmology. And this is starting to be recognized by many researchers. Perhaps the most fundamental predictions of the Big Bang hypothesis derive from the idea that the universe started at a highly hot and dense period as a completely homogeneous and isotropic cosmos. From that, we can derive the idea that in the theory, large-scale structures, galaxies, clusters of galaxies, so on, derived by the gravitational collapse of initially very tiny irregularities in this hot plasma. Since the Big Bang hypothesis says the universe formed 13.8 billion years ago, if we look out into the universe and see the velocity at which objects are moving in the universe today, we can mathematically derive what the biggest objects in the universe are. And we're freezing again. What we found, what everybody has agreed to, is that those biggest objects should be no larger than 1 billion light years. Now, 1 billion light years certainly sounds like a fairly big distance, but if we look out into space, as our telescopes got more and more powerful, we saw greater and greater conglomerations of matter. It's interesting historically to say that back in the 1930s, when this hypothesis first was put forward, there was no evidence that at the largest scales, the universe was homogeneous, and therefore there were no large objects beyond 1 billion light years. And as the evidence accumulated, we didn't see any evidence of this convergence to 1 billion light years. Now, it isn't just me saying that 1 billion light years is the limit. Even such pioneers of the Big Bang as Joseph Silk said back in '88, if you saw large objects extending over 1,000 megaparsecs, that's 3 billion light years, you would have to question the Big Bang theory. Well, what has happened now is that we have seen the discovery over the past decade of many objects that exceed this limit. Just to start with the most recent example, at the last American Astronomical Society meeting, Alexis Lopez demonstrated the discovery of a 3 billion light year arc of galaxies, an arc so big that in the sky it extends about 15 degrees, 30 times the diameter of the full moon. But this discovery is only the most recent of a chain that have been published in the peer-reviewed literature. For example, the Cosmos satellite, which was looking, the Cosmos survey, which was looking at a very small part of the sky, but looking very deeply out into space and back into time, discovered conglomerations of galaxies that stretched over many gigaparsecs, so 3 to 6 billion light years. And this graph shows the concentration of galaxies as you go out into redshift, showing major differences in density over extremely large distances. Other surveys of, for example, gamma ray bursters, which can be seen at great distances, show that they too have concentrations in the sky that cannot be explained as statistical variations and extend over billions of parsecs. So all of this data presents a severe challenge to the idea that there was a Big Bang, because we can flip the equation and say, how long did it take, at a minimum, to form these structures? And it must have taken at least 100 billion years. So this is a major challenge in the sense that the clear predictions of the theory are contradicted by multiple data sets. Now, there's a second very important, but not too publicized prediction of the Big Bang. Obviously, the Big Bang assumes that the universe is expanding, that the explanation for the well-known observed Hubble relationship between the shift to the red of light from distant objects and their distance, the explanation for this observed phenomena is that the universe is expanding. Now, there are some direct geometric consequences of the idea that the universe is expanding, and that's the reason for the Hubble relationship. The most important of these is what's called surface brightness dimming. Now, the surface brightness of an object is easy to explain. If you take the apparent luminosity of an object on the sky and you divide it by its apparent area on the sky, that's its surface brightness. If you have ordinary space, which is not expanding, and you move an object like a lamp twice as far away, its apparent area will contract by 2 squared, 4, and its apparent luminosity will go down by 2 squared, 4. Therefore, the ratio of those two numbers, the surface brightness, will be a constant independent of distance. So the surface brightness of an object in non-expanding space is independent of its distance. But in expanding space, this object was closer to us when the light was emitted, and therefore it looks larger. So its apparent area on the sky is increased, and its apparent luminosity is decreased because as time is stretched, there are fewer photons arriving per unit time. The net result is that in an expanding universe, the surface brightness of objects goes down as the quantity 1 plus z cubed. Well, my colleagues and I, Dr. Ricardo Scarpa and Dr. Renato Fulamo, have for many years studied this and published our results in peer-reviewed journals, looking at what is the actual surface brightness of galaxies. And we find that the surface brightness data is an excellent fit to no expansion. So this plots redshift versus the logarithm of the surface brightness of galaxies. So this is a factor of 10, a factor of 100, a factor of 1,000. The red line is the Big Bang prediction. And these dots of various colors are dozens or hundreds or even thousands of measurements of actual galaxies going out into space by the Hubble telescope and other telescopes. And what we find is that the slope is insignificant. So there's an excellent fit to the zero evolution of no expansion. For equal luminosity, the galaxy's apparent radius would be constant to 1%. So this is a tremendous contradiction to the very idea that an expansion is occurring. And this has been published in the biggest journals. And there are counter arguments where people say, well, the explanation is the galaxies were really, really tiny, and this completely nicely compensates for the expected surface brightness dimming. And in the question period, we can get into why that can't possibly be the case. But this is, again, a fundamental contradiction of the very idea that the universe is expanding. Well, what people have been mainly hearing about in the crisis of cosmology coverage is the contradictions that arise from the study of the cosmic microwave background. Now, the cosmic microwave background, this very dim radio glow throughout the universe, has been cited as a key proof that the universe was once billions of degrees hot, even though the actual observed temperature is 2.7 K. So this is quite an extrapolation by a factor of trillions and trillions. But the theory makes certain concrete predictions that really can't be changed about the very small fluctuations that occur in the brightness of the cosmic microwave background as you look at various points in the sky. And if you look at various points in the sky, you find that in contrast to these predictions that the fluctuation should be random or Gaussian and isotropic, the same all across the sky, they're not. So this is a map based on the observations by the Planck satellite of very small fluctuations. This is of the order of tens of microkelvin across the sky. And the red areas are slightly hotter, slightly more intense. The blue areas are slightly colder, less intense. Well, you can see by these large scale fluctuations or large scale on the sky that they aren't random. The fluctuations actually lie almost in a plane. And they aren't isotropic, because if you look at the fluctuations on the left-hand side of the drawing, they're much smaller than on the right-hand side. Now, this seems to align either perpendicular to the ecliptic, which is the curved line, that's the plane of our solar system, or is almost parallel to the plane of our galaxy. Now, that shouldn't be happening at all, because of course, in the Big Bang theory, this radiation is coming from billions of light years, far from our solar system or our galaxy. But there are many individual ways of measuring this that all add up to the fact that this is not random, this is not isotropic, and this is not in accord with the predictions. Now, there is one exception to these predictions, that on the very largest scales, there should actually be correlations. So there's a very interesting prediction because it's quite concrete. So the Big Bang theory, as modified by inflation, dark matter and dark energy, predicts that the correlation of intensities on the sky, of course, will be very high when the distance between the 2 points being correlated is low. That's to be expected. But what isn't expected is that this theory predicts that there should be negative correlations at about 60 degrees apart on the sky and positive correlations at 180 degrees. So there should be more than random correlation when you look at opposite sides of the sky. Well, the blue line is Planck's observations of these correlations. And what you can see easily by eye, and it's confirmed statistically, is that the correlations that are predicted just don't exist. And I took the same data and I divided the predicted, the observed amount of correlation by the predicted level. So the predicted level is unity. And this is the actual observed correlation. And you see, except for the areas where both curves cross the axis, and of course their ratio becomes not significant, the correlations are much lower, about a factor of 5 lower than predicted, and are quite in accord with no correlation whatsoever. So these are fundamental contradictions of the quantitative predictions about the cosmic microwave background itself. But there are other contradictions. So if we look at the precise measurements that have been made by the Planck satellite of the degree of correlation at various scales, the degree and fluctuation, excuse me, at various scales on the sky, this is a plot of how much amplitude of fluctuations there are at various scales. And this is measured in spherical modes. So the more the spherical modes down here, that means the greater number of pieces you're dividing up into the sky and see how much fluctuation there is at smaller and smaller scales. So the blue dots are observations. Now the present theory has 9 fitting parameters or free variables that cosmologists can use to make a nice fit to this curve. So in this right-hand part of the curve, you do have a very nice fit, but then again, you have 9 free variables to make that fit. When you get to the larger areas, you sort of have this embarrassing dip where there isn't much of a fit at all. But the most interesting thing is these free parameters that cosmologists use to fit this curve make predictions about other data sets in the universe. So these free parameters are things like the Hubble constant. So you fit the Hubble constant to this curve, you get a prediction of what the Hubble constant is. What is the relationship between redshift and distance? Well, of course, that can be measured by actual observation. And the measurements based on supernova and other data points over the past 20 years have pretty much nicely converged in this upper curve and have converged around 72 kilometers per second per megaparsec, which is the units they use. But the problem with the predictions is they started out being pretty close to observation. And as the observations of the microwave background got better with Planck, the predictions diverged. This is what people call the crisis in cosmology, because of course, there's a prediction that is now wrong by approximately 5 sigma, by a very big margin. So that's in addition to all of the other contradictions I've outlined. Another big parameter that is predicted by this fit is the density of the universe in ordinary matter, baryonic density. Now, why is that important? Well, since the Big Bang predicts that the universe started with a hot, dense conglomeration of matter, that necessarily produced fusion reactions. So you necessarily produced certain amounts of light elements, helium, deuterium, lithium. And the amount is determined by the density of the universe at the present time. So you can predict, and people do predict, the amount of helium, deuterium, and lithium. Well, for deuterium, gee, there was good news for the Big Bang theory, because this is the one data set that the theory fits very well. It does accurately predict the amount of deuterium, the heavy isotope of hydrogen, observed in the universe. But for the other two predictions, helium and lithium, it's way off. So the prediction for helium is 24%. So there should be stars and galaxies that have more than 24% helium, because helium is produced by fusion reactions in stars, but there should be none that is less. Well, if we look at stars that are close to us, what we find is that lots of these stars have helium abundance that is far less than the predictions, which is the red line. You have helium abundances down to 11%, even down to 5%. And this has been known for at least 10 years. In the case of lithium, the situation is even worse, and this is known as the lithium problem. Lithium abundances decrease towards zero as we look at stars that have less and less iron and other materials, elements that we know are made by stars. So as we look at more and more pristine stars, the level of lithium drops to about 1/20th, or compatible with zero, compared with the predictions of the Big Bang, which are up here with those red lines. So again, very fundamental prediction that can't really be altered, and complete disagreement with the observations. I don't have time to give a comprehensive list, but if you just look at some of the most prominent ones that have developed over the past 20 years, and especially over the past 5 years, you have all these disagreements between predictions and observations, just dealing with the CMB. And the chances of these being random, due to a small sample of data, 5 in a million, 3 in 10,000, 3 in 10,000, these are almost impossible to be due to chance. If you add them up, all up, of course, by multiplying the chances, these are independent data, it becomes impossible that these are due to random variations in the data. So right now, we have the situation in 2021 that the Big Bang hypothesis predictions are in conflict with observations of 16 independent data sets and are in agreement with only one, the one I mentioned, deuterium abundance. Now, this isn't just me speaking. If you look at the published peer review literature, you have people pointing out these individual discrepancies over and over again. For example, recent publication in Nature Astronomy, a prominent publication, these inconsistencies between disparate observations show that the flat lambda CDM, so that's the dark energy, dark matter model, the current model of the Big Bang, do not seem to any longer provide a good candidate for a concordance cosmology. Another set of observers say, here we have argued the Hubble tension could be another manifestation, yet another manifestation of the breakdown of the FLRW model. Well, what is that? That's the Friedmann-Lemaitre-Robertson-Walker model. It's a scientific name for the expanding universe Big Bang model. So, does that mean that other people or anyone is saying in peer-reviewed, published journals, as I did 30 years ago, that the Big Bang never happened? Well, the answer is no. Actually, nobody is saying that, not even me. I haven't said it in a published peer-reviewed publication since 2003. And the reason is, and I have had this on high authority in writing, that leading journals on policy will not publish any argument that the Big Bang never happened. They will publish various contradictions with various parts of the theory, but they will not publish an overall survey. Now, we can get in the question period of why this is the case, but at the moment, the situation can be described by what I call the ENC effect. So the ENC effect is the emperor's new clothes effect. So it's like you can say, I see the emperor's elbow, I see the emperor's knee, or even I can see the emperor's rear end. But you cannot say in a published peer-reviewed journal, that's because the emperor's wearing no clothes. Because if you do say that, you're either stupid or unfit for your job. So that's the situation today. We're not in a published peer-reviewed journal. So I can tell you today, the Big Bang theory is wearing no clothes, and the Big Bang did not happen. So let's break here for 5 minutes and I'll take a few questions and then we'll get into what did happen. So don't ask me questions about what did happen. We'll get into that shortly, but I'll take a few questions about what I've presented so far.
I also have a chat line. You can put your question in there and I will read it. Okay, if you can go into the chat line, there's Mike. It says, can you in the question answer why those who control the published peer review think they're still doing science?
Well, I think that it's a complex sociological problem that has happened over the years. But basically, you have a field in which the funding is controlled very centrally. You don't have a lot of funding sources for cosmology. They're basically, it's funded by a few government agencies in most countries, like our NASA and our National Science Foundation. So when you have centralized funding, you have the possibility for orthodoxies developing. Orthodoxy developed where basically the people who are allocating the money are theoreticians who have spent their entire lifetimes developing these theories. And as is natural, they're human beings. They don't want to see these theories contradicted. This spreads to a wider circle because there's basically an alliance between media journalists who think this is a great story. It's a wow, gee whiz story, dark energy, dark matter, things we don't understand, and the people who control the funding. So the net result is you have an overall climate where even people who aren't dependent on funding, and most of these big publications are private publications, they fear their reputation. They fear the overall concordance, as it's called, bureaucracy will attack them if they break with that. And that's the fear that's sort of holding back the field. So even though individual contradictions are being published, the overall paradigm change, which is necessary, is being held back.
Okay, we're getting quite a few questions here. Can you see the chat line or do you just want me to keep on?
Why don't you just read the, as long as I'm full screen, I guess I can.
Okay, that's fine. Jeff Cole had one. Will the DSI study shed light on all of this?
The which study?
As the DESI study?
Oh, DESI, yeah. Well, that was actually the last contradiction. So that contradiction from the so-called dark energy survey, And that's, again, interesting propaganda. They're not surveying dark energy. They're actually surveying real galaxies and deriving mathematically conclusions about dark energy and dark matter. But they have found that matter is more concentrated than the theory predicts. Now, this is actually sort of almost icing on the cake, because this is not a huge contradiction. This is about a 1 in 20 chance that this could be caused by random variation. But it's of concern because it's on top of all of these other contradictions. So it's, again, the question, the theory isn't getting anything right. There are no recent data sets that they can point to other than the deuterium, where they can say, we made these precise predictions and they're precisely right. In the case of the DESI survey, in the case of everything else that's come out over the last 5 years, predictions are precise, but they're precisely wrong.
I had a question from David Paris. Please explain how the size of point light stars is calculated.
I couldn't get the end of that sentence, sorry.
Please explain how the size of point stars is calculated.
Okay, well, stars are too small to use as the source of this surface brightness test. We're using the size of entire galaxies. So galaxies are so big that even if there are extreme redshifts, up to redshifts are 8 or 9, so many billions of light years away from us, our best telescopes, like the Hubble telescope, can still resolve the largest of them. So in our study, we simply took the brightest galaxies, which are the largest galaxies, and we made a study of them. So there you can make they're very easy to measure because they have, especially spiral galaxies. Spiral galaxies have this interesting characteristic that their light falls off exponentially. So if you plot it as a logarithm, it's a straight line fall off. So you can measure their diameters very precisely, and that's how you get it. Stars would not be, only a few stars can we measure their diameters, so that would not be a good test. But with galaxies, we can measure them pretty easily. Why don't we take one more question and then I'll do the second part, okay?
All right, let me run through these and see. A lot of them are kind of the same.
Wait,
Okay, question from Mark Lofts about redshift. Is this, maybe this could be Doppler shift? What's the explanation for redshift again?
we'll get into that in the next section. But I will be back in 2 seconds because I just noticed I did not fill up my water. I will be right back. Okay, so what happens if we get rid of the hypothesis of the Big Bang? What happens then? Well, the first thing that happens is we can eliminate these imaginary entities that the Big Bang now requires that have no experimental or observational validity in the laboratory. We can get rid of inflation, we can get rid of dark matter, we can get rid of dark energy. And I have to agree with Joseph Conrad that if the universe were really composed of 99% dark entities that we don't understand, it would have been too dark too dark altogether. Instead, without the Big Bang, with one exception, we can say that the basic processes in cosmic evolution are controlled by processes that we have observed and can understand on the basis of laboratory experiments and our observations in the solar system with our experimental devices traveling throughout the solar system. These processes basically come from electromagnetism in plasmas. Plasmas are gases in which electrons can travel freely. And the vast majority of the universe we observe are plasmas. Stars are plasmas, and the space between stars are filled with plasmas. So I'll get into these effects presently because I don't expect people to be familiar with them. In addition to electromagnetism, we have, of course, gravitation, and we have nuclear reactions, especially fusion reactions. So let's look at these principles and see how we can understand cosmic evolution. Now, of course, cosmic evolution from when? From the beginning? Well, if there was no Big Bang, there was no beginning. We have to instead start from the farthest back we can look. And this takes another viewpoint to how we describe the universe. As Hannes Alfvén wrote, to try to write a grand cosmical drama leads necessarily to myth. To try to let knowledge substitute ignorance in increasingly large regions of space and time is science. That means what we do is we look farther and farther out into space, farther and farther back into time. So when we start a story, it's not starting at some mythical beginning of the universe, which there is no such thing. It's simply the earliest time we can look at with our present knowledge. With our present knowledge, we can look back to a time in which the universe, with basically the same density of matter that we have today, the same energy density that we have today, was relatively homogeneous plasma. And we know one phenomena that had to exist in this plasma, and that is the pinch effect. Pinch effect is a very basic effect that was discovered by Ampere 2 centuries ago. And it basically says that if you have two currents moving in the same direction, they create magnetic fields which draw those currents together. If the currents are moving in the opposite direction, the same process pushes those currents apart. So if you imagine any plasma today or in the past in which you have tiny random currents, those currents will slowly grow because the currents that happen randomly to be moving in the same direction will pull together to form larger currents, and they will repel the currents moving in the opposite direction. So you will build up over large periods of time, and now we're talking trillions of years, from tiny currents, cosmologically significant currents. The second thing we know for certain about the situation in such a plasma or in any such plasmas is that the conductivity, the ability of electricity to travel through these plasmas is anisotropic. It's much easier along the magnetic fields than across. It's a little complicated to explain, but it's very fundamental. Because of how magnetic forces work, any charged particle circles around the direction of the magnetic field. Now, if we connect the directions of the magnetic field, which is a real thing in the world, we get an imaginary line called the magnetic field line. So it appears these electrons are circulating around the magnetic field lines. If the magnetic field is sufficiently strong and the plasma is sufficiently dilute, less dense, then the time it takes to circle around is going to be very small compared with the time it takes for one particle to run into another particle and collide. It's only through these collisions that a particle can move across the magnetic field and move to another field line. So that means it's much easier for currents to travel along the magnetic field lines, and in the end, currents only move parallel to the magnetic field. Well, as a consequence of this, and there's a straight electromagnetism, the basic way currents have to move through the universe is in force-free plasma vortex filaments. This was discovered many decades ago. So a force-free magnetic filament means that you have a filament in which the currents move straight along the axis, but at the outside of the filament, they're moving perpendicular to the axis. And in between, they're moving in helices that get looser and looser as they approach the axis. And if you do the mathematics, you find that that means the magnetic fields produced by the currents at each point lie in the same direction of the current. So this is a basic secret of the universe, that the universe is built up out of mainly plasma vortex filaments. This isn't the universe according to Eric Lerner, or even the universe according to Alfvén, who was the first, together with his colleague, Dr. Feldhammer, to point the importance of these vortex filaments. This is something that must occur if Maxwell's laws are correct. So this is the universe according to Maxwell. And if Maxwell's wrong, the light shouldn't be on. So we know Maxwell was right. The Veil Nebula is an excellent example in the present day universe of what these vortex filaments look like. This is a Hubble photograph with enhanced colors of the Veil Nebula. And it shows a hierarchical or fractal vortex filament. So you see the current lines, the plasma, arrayed in a helical filament around the outside, the currents moving straight lines along the axis of the filament. And if you look closely at all of these subfilaments, they have the same structure. They have the helical structure and the straight structure, the same as the overall filament. Now, as these vortex filaments built up, they must have been affected by gravity. Gravity does not scale the same way electromagnetism. It has greater and greater effects at larger and larger scales. We see this, of course, gravity between ourselves is insignificant. It takes large objects like the Earth to have significant gravity. Once gravity started to affect these vortex filaments, they started to contract along their axis. Now, they didn't contract very much across their axis because these vortex filaments are spinning. And of course, there's conservation of angular momentum. So an object that contracts spins faster. And eventually that spin counteracts gravitation and prevents contraction across the axis. So you ended up with disk-like formations. And then you had a new electromagnetic phenomena, which is the homopolar generator process, also known as the Faraday disk generator, after Faraday, who discovered it. If you have a conducting disk moving in a perpendicular magnetic field, there is generated a potential between the outside and the inside of the disk, a voltage which accelerates a current between the outside and inside of the disk. So what that adds up to is the production in these primordial vortexes, a larger filamentary current of smaller sets of perpendicular filamentary currents. So you get perpendicular filamentary currents. All of this was hypothesized by Alfvén basically 40 years ago, and was developed in part by collaborators, including myself. You get these perpendicular filamentary currents that can conduct angular momentum to the external plasma and subtract angular momentum from the contracting disk. So because these filaments can push the plasma very effectively, on the outside, the angular momentum of the disk decreases and you can get much larger gravitational contraction. So this sets up a hierarchy of smaller and smaller units. Back 30 years ago, one of my colleagues, Tony Peratt, a student of Alfvén, used a supercomputer to trace this process on the scale of a galaxy. And he shows in this supercomputer simulation how two blobs of plasma can rapidly accelerate each other into the characteristic plasma shape of a spiral galaxy. And if you viewed this at a slower rate, you would see that these spiral arms are actually filaments themselves that are rotating. We see, with 30 years of experimental and observational data, we see this hierarchy of filaments in quantitative detail formed at all scales. This is a image from ALMA of filamentary structure at the level of 0.05 light years. These are star-forming clouds that are all filamentary in structure and have the same strong magnetic fields, half light year. And if we go all the way up in scale, we see plotted 5 million light year radius. So this little radius across these red lines is 5 million light years. And these are hundreds of millions of light years long filaments formed of galaxies. So these are the evidence for these primordial vortices in the structure of the present day universe. Now, I said that this happens if there's strong enough magnetic fields relative to the density and temperature of the plasmas. Well, people have made observations of plasmas at the scale of intergalactic medium, clusters of galaxies, molecular clouds, and even protostellar disks out of which stars like our sun condense. And at all those scales, the magnetization ratio is orders of magnitude more than unity. And that means that these phenomena must work as we have described in a very anisotropic, very inhomogeneous way. The exception is when you get down to the scale of stars. Stars are sufficiently dense that collisions happen more rapidly than the orbits around magnetic field lines. So stars don't break up into smaller objects and are governed by different processes, including, of course, the process of thermonuclear fusion, which produces the energy that drives further evolution. Back 30 years ago, and more recently, I showed that from basic plasma principles, you can derive the basic quantitative size and scale of various objects in the universe. I don't have time to go into this, but this plots evolution of galaxies, plotting the density times the radius versus the density times the radius squared. And in summary, what it shows is that clusters, galaxies, and stars must evolve with the scales that are actually observed, which is these boxes up here, simply based on basic plasma theory combined with the laws of gravitation. From this basic plasma formation of structure, you can derive a model for the formation of stars in a galaxy. Back in 1989, that's what I did. And again, just briefly summarizing, this involves the production of very large supernova-producing stars only in a thin disk. Most stars in a forming galaxy form in a large halo where stars that are between 12 and 4 times the mass of the sun burn hydrogen to helium very rapidly. So this model predicts the correct amount of helium and the correct amount of deuterium and lithium produced by cosmic rays produced in forming galaxies. So obviously, even though the universe had no beginning, every object within the universe did have a beginning. Galaxies had beginnings, stars had beginnings. So what we found is that you can produce not only structures, but the right amount of light elements. And when I updated this last year, I'm still trying to get these results published, but I presented them at the American Astronomical Society meeting right before the pandemic. We can see that both the earlier and the updated version of this model produce the correct amounts of deuterium, helium, lithium, and 2 other elements, beryllium and boron, that everyone agrees are produced by cosmic rays originating from stars. Another big observation that confirms this theory is when we can look at galaxies that are forming. We can see them in the present day universe, or we look out into the distant universe and see how they were billions of years ago. These are called ultraluminous infrared galaxies because they're very bright. And just as was predicted, we find that relative to their mass, they're producing something like 100 to 200 times as much helium per unit time as is being produced by our own sun. So that produces in a period of 100 or 200 million years, while these galaxies are forming, all of the helium that we now see. And it also explains why in stars formed earlier in this period, the helium is not as much as those formed at the end. Well, this gets into the cosmic microwave background. It's been known for decades that if you calculate the energy that must have been produced by changing the observed amount of hydrogen into the observed amount of helium, you get the energy in the cosmic microwave background. Turns out that's about 4 million electron volts per proton. We know, because we can observe it, that this energy is being thermalized to dust within these baby galaxies. Baby in the sense of young galaxies. So they're very dusty galaxies, and the energy is thermalized down to 20 K. Well, but how does it get thermalized and spread out throughout the entire sky? Well, I and others developed theories of this based on what happens in the center of galaxies. In the center of galaxies, we have converging electric currents. Those currents we know from laboratory experiments, I'll get into that in a minute, form twisted little bundles of vortex filaments, which have been named plasmoids. And these plasmoids have additional instabilities, which we've studied in the lab, which produce concentrated beams of ions moving in one direction and electrons in the other direction. So this is an artist's conception of the plasmoid in our lab, producing a beam of electrons and ions, which we observe. And this is observations by the ALMA telescope of M87 galaxy producing a beam which is viewed so that the magnetic field direction is shown by these stripes and shows that it is a current, an enormous electric current that's confined by its own magnetic field. Well, as we said earlier, this vortex filaments form a hierarchy of smaller and smaller filaments. And we know again from electromagnetism that these very tiny filaments, tiny in astronomical terms, can absorb and re-emit microwave frequency radiation. So you basically have a radio fog of these tiny filaments that are taking microwave radiation originally emitted from stars and from these clouds around galaxies and scattering it across the entire sky. What we're observing when we look at the microwave background is a radio fog, not the supercooled remnants of the Big Bang. Well, what's the evidence for this? The biggest evidence is that the universe is not transparent at microwave wavelengths. So astronomers know that there is a close correlation between the IR, infrared luminosity of galaxies, and their radio luminosity. But what I found starting 30 years ago, and I've updated it recently, is that, and this was published in Astrophysical Journal originally, as you move away from Earth, as the distance from our position increases, this correlation shifts. So this plots the radioluminosity at constant IR luminosity versus the log of distance from Earth. And that radioluminosity drops by over an order of magnitude, correlated with distance from Earth. Now that's totally impossible unless the universe is not transparent. It's transparent in IR luminosity, in IR frequencies, but it's not transparent in microwave frequencies. So this is direct evidence that we are living in a microwave fog. And I can go into the question period, but we've also seen direct evidence of observation of some of these tiny filaments. So to summarize, all cosmic processes can explain with lab-tested physics, except the Hubble process. The Hubble process is the one thing where we too, without the Big Bang, have to hypothesize that a presently unknown process is causing photons to lose energy with distance. There's no known plasma process that could cause this. But this doesn't have to be like dark energy. We can study this in our solar system with the technology we now have. We could put up satellites that could measure at distances of millions of kilometers a redshift and measure how that redshift changes with distance. And that redshift, if it was due to the Doppler expansion, would not be present in the solar system at all. So that's the one thing I would say we don't have explained. Well, finally, what does this all have to do with us right now? What difference does it make whether the Big Bang happened or not? Well, I think there's three big ways it influences us here on Earth. Obviously, right now in 2021, humanity is in a crisis. This is the most serious crisis we've faced since the Second World War, and basically in the lifetimes of almost all of us present here today. If you think that this is just a blip caused by the pandemic, I think this graph is a good way to see this is the outcome of decades of growing problems. The blue line charts the rate of annual decline in the mortality of human beings. So that peaked in the 60s. That was the fastest rate of decline of mortality. So the fastest rise in living standards. And that curve has been on a long downward slope towards growing stagnation. It's a little blip during the 21st century as China was integrated into a world economy. And of course, in the past 2 years has turned negative. The rate of mortality has been increasing. The red line shows the rate of energy increase corrected for the population growth. And again, this peaks in the 50s and the 60s and declines more or less in tandem. So what we have is a growing stagnation, a decrease in the development of the society over a long period of time, culminating now in a crisis in which standards of living are declining. Ending this crisis requires many things, but one thing it requires is energy. We need more energy, cheaper energy, so that we are not drawing vital resources away from healthcare and other things that we need to maintain the health of humanity. We need cleaner energy so we are not polluting the skies and weakening our lungs to make them more vulnerable to viruses like COVID. That means higher energy density, more energy out of less fuel. And the only thing that fits the bill is fusion energy. And if you're not convinced of that, please see our LPPFusion videos that I've highlighted at the bottom of this slide. What's the connection between fusion energy on Earth and cosmic evolution? To use the power that drives the universe, which is fusion energy, we need to understand those same processes that drive cosmic evolution. The pinch effect, anisotropic conductance, filament formation, plasmoid formation. Those are the key effects we need to understand to get fusion energy. For the tokamak device, which is the dominant device that most money is being put into, filaments lead to disruption. And they're pretty much impossible to control. So this is a great photograph of plasma inside a tokamak showing the filaments, and this big filament is disrupting the plasma. However, there are other devices, such as the plasma focus device that LPPFusion works with, in which we use the filaments to actually produce fusion. So in this little, in this device, we dump a lot of electricity into a very small place in a very short time. And this is what happens. First, these filaments form through the pinch effect, and they project themselves down our anode. And these objects are only centimeters across. By the magnetic field and the electric currents interacting. When they get to the end of the anode, they funnel into a hole in the anode, and the pinch effect pinches them together into a single filament, much hotter and much denser than what we start with. The kink instability pinches them horizontally or along the lines into a plasmoid. And thanks to Torov Greek for this excellent animation showing the physical processes. This plasmoid, through its own instabilities, heats up to the point where fusion reactions start to take place. And through the instability I mentioned earlier, enormous electric fields are produced in the center, which accelerate beams of ions and electrons, which take the energy out. That means we can actually collect this energy, which is moving electricity, directly without putting it through the expensive process of boiling water and producing steam and running turbines. This is not just theoretical. We have seen these filaments and photographed them. This is an ICCD 0.5 nanosecond exposure of filaments going up the side of our device. You can see these 100 micron radius filaments. And then on the right, you can see a 200 micron radius plasmoid, which we photographed in our device. And we produce these plasmoids in most shots. Because we are using these cosmic processes rather than trying to fight them, we actually have obtained better results by a factor of 1,000 than any private fusion effort. And we are almost up to the level of the biggest government effort, which is the JET tokamak, even though we've only spent 8 million and they've spent about 1,000 times as much. We are using PB11 fuel, which is going to be safe, no radioactive waste, compact, cheap, and decentralized. And the fuel, if necessary, could be obtained from seawater. I'm about to wind up, but the second way, important way that we need to end the crisis is we must win humanity as a whole to rationality, to the scientific method. I don't think that really needs reinforcement. But as Alfvén pointed out decades ago, one of the worst aspects of the Big Bang theory is to make science look like science fiction. Science became increasingly presented as the negation of common sense. The limit between pseudoscience and science tended to be erased. And it was difficult to find any difference between science and science fiction. So this is the sort of wow, gee whiz, that we don't understand dark energy, we don't understand dark matter, we don't understand inflation, but this is what's running the universe. This is the confusion of science with mysticism. If we abandon Big Bang, we can say the universe can be understood in a common sense way, using the same technological and scientific concepts that we use to run our basic technology here on Earth. So scientific credibility doesn't become a matter of whether you trust scientists, but whether you trust rationality. And finally, in such a crisis, as much as we need energy, we need hope that we can escape from this crisis. Cosmic evolution, understood without the Big Bang, is running up, not down. If we look at the flows of energy in these various scales, we see that the flow of energy has increased over cosmic time and increased at an increasing rate. If we projected the evolution of life on this chart, we would see the same tendency. Unlike the Big Bang universe, which is sort of expiring from an enormous bang at the beginning to a petering out over time, the non-Big Bang universe is running up, not down. It is a universe that gives us rational reason to hope. So that's where I would like to end. Thank you very much for your attention for a long presentation. And we have time for questions up to 9 o'clock, 10 o'clock Eastern time, 9 o'clock Central, and so on. Thank you very much. David?
Okay, let's see. Have you heard of cases where high redshift quasars interacting with and even in front of low redshift galaxies catalyzed by Alton ARP?
Right. Well, yes, I knew Chip Arp. He was a fantastic astronomer, a fantastic guy. And he certainly suffered by what can be called the groupthink of cosmology and actually had to relocate outside the country to Germany to do his work. I think that if you look at the quasar data overall, there is some sort of Hubble diagram. In other words, in general, quasars that have higher redshift tend to be dimmer than those that are closer. That implies part of the quasar redshift is like the galaxy redshift due to their distance. It doesn't mean that it's due to expansion, but it is correlated with distance. There's an enormous scatter, much greater among quasars than among galaxies. It's certainly possible that part of that scatter could be due to processes that are very close to the quasar itself or part of the quasar. So I would say this is an open question. It certainly hasn't gotten the attention it deserves because ARP was basically dismissed as a heretic, something that happens to a lot of us. But I would say that it needs a lot more study. It's certainly an open question.
Question from Charlie Ross. Does your cosmology theory allow for the expansion of space or space-time?
Well, it's not a question of theory. I think the observational evidence does not allow for expansion to be the explanation of the Hubble relationship. Basically, expansion geometrically, no matter what's driving the expansion, you have to have this surface brightness decrease. And the data does not allow you to have it. And let me just briefly go into the counter explanation that there are these teeny tiny galaxies that by a gigantic coincidence happen to be intrinsically brighter in just a way to cancel out the surface brightness dimming that's expected. The problem with that is that we can look at these galaxies and we can measure their luminosity. Now, the slide I skipped over because I was running a little late is that if you look at the static universe model, in which some unknown process is simply linearly producing a redshift with increasing distance, and you compare that to the supernova data, you get an amazing coincidence, which is that that line, which is the bottom continuous line from the static universe hypothesis, is almost identical to the dashed line from the Big Bang hypothesis, which includes dark matter, dark energy, inflation, and so on. This is just, these are equally good fits to the data, which are these dots, which is the actual observed supernova luminosity versus redshift, apparent luminosity. So basically, the luminosity, the model does not matter. The luminosity is the same in both models. Well, that can give you the stellar luminosity and the amount of star mass in a given galaxy. Now, you can determine the total mass of the galaxy by measuring spectroscopically how fast that galaxy is rotating and by measuring its diameter, where the two models differ. Because the diameter in the Big Bang model is going to be teeny tiny. The diameter in the static model will be the same as galaxies in the present universe. If you look out far enough, you get a contradiction with the Big Bang model. The mass of gravitating matter in these distant galaxies with Big Bang assumptions becomes smaller than their stellar mass, which is obviously impossible, unless you want to hypothesize negative dark matter, which has negative gravitation or something like that. So you get contradictions. So basically, observations rule out an expanding universe as the explanation for the Hubble relationship. Something else, which is a process that's currently unknown, must be changing the light as it travels. Okay.
Thank you. We had a question here. Where did the first hydrogen atom come from?
Well, this is as far back as we can look right now. In other words, the structure of the universe as we observe it today gives us evidence for the structure of formation, the formation of structure from an initial plasma made of hydrogen, basically a plasma made of protons and electrons, which together make up a hydrogen plasma. If you want to go back further, we need more evidence. Excuse me. It's certainly not impossible, but at the moment it's speculation. For example, we could envision an earlier stage of the universe in which the matter density was smaller, but the energy density, the density of individual particles was larger. So then there would be pair production, leading eventually to the production of plasma. Hannes Alfvén did look into the dynamics of what he called an ambiplasma, because in such a high energy plasma, and this is not like the Big Bang, high energy density, this would be the same energy density as the present universe, but individual particles could have high energy. You would produce equal amounts of matter and antimatter. Now, we don't see that in the universe today. The universe that we can see is entirely, almost entirely matter. Antimatter is observed, but it goes out of existence almost immediately. Well, he and his colleagues looked at this back in the 1970s and 1980s, and they found that there were clear, understandable plasma processes that, working together with gravitation, would actually produce a cream separator in which the matter and the antimatter would actually be moved away from each other and be separated from each other. And the borders between this, the antimatter and matter regions, would be actually so dilute, so non-dense, that they would be very difficult to observe. So he actually did create a speculative scenario for an earlier stage of universal evolution. So it's not impossible, but at the moment we have to say, we don't really have any evidence for that stage. If we found evidence of antimatter conglomeration somewhere in the universe, or the borders between matter and antimatter, then we might be able to go back further. But again, what I want to emphasize is the idea that you have to know where there are turtles all the way down, as the joke goes. No, that's mythology. Science means we go back step by step as far as the observational evidence takes us.
Okay, we had a question. How can we avoid letting worries of ego let us forget to be curious? How do we navigate the knowledge around us if it's possible we're unspoken intentions behind?
It's possible what?
Yep.
I have a philosophical question. How do we put aside ego to be curious?
Right.
I knew I was going to do that.
Only through a good social process. Science is a social process. It is a cooperative process. The idea of some scientist alone in his, and this is sort of the caricature of Einstein, alone in his office, writing equations on the blackboard and coming up with, the stroke of genius. That's wrong. Science is done cooperatively. You can only cooperatively arrive at useful predictions that you can use to understand nature and eventually use it in technology. What happens is that social process can go wrong if two conditions exist. One is a shortage of resources. In other words, there's competition for resources to do science, money. And two is over-centralization of the allocation of resources. If you have a situation where there are a lot of people funding a field, it's very difficult for people to become orthodox. It's very natural for people to support their own theories. We're not going to change that part of, human endeavor. But this is a self-correcting process if you have a social process in which people who are funded from many sources, published in many sources, can interact. And for example, I think in the biological sciences, where there have been orthodoxies, it's easier to overthrow orthodoxy because there are more sources of funding. There's more abundant funding. There are 4 times as many biological scientists right now as there are physical scientists. In cosmology, you have a bad social system because, one, you only have a handful of sources of funding. There's sharp competition for this funding because there's so little of it relative to needs. And on top of that, you have cosmology is a part of science that has strong links to the rest of society. Cosmology is about the whole universe. It is always being linked to people's views of religion, people's views of society itself. So you actually have resonances between social evolution and cosmology, which Alfvén was put this into the model of the cosmological pendulum swinging back and forth over the centuries between myth and science, influenced by what's happening in the society. So what I and many other colleagues have advocated, we published almost 20 years ago an open letter in New Scientist in which we urged that funds be set aside for funding non-orthodox cosmological research. And I think that has to be done. The only path forward is if there's a decentralization of funding, possibly coming out of advances in fusion. People will see that cosmology and astrophysics do have applications here on Earth, which will make people more eager to fund research that now is being funded in too narrow a way. And that's the way the social context of cosmology will be changed.
When will your machine make a net gain in energy?
Well, thanks to the internet, I'm on record of making several wrong predictions as to how long it's going to take us. So I won't say how long it's going to be. I will say, if everything goes right, it should not take us very long. Our plans are to complete this phase of the experiment in the coming 12 months. So if everything goes right, it would be 12 months. But I'm not predicting it will be 12 months because, unfortunately, in research, it's very rare that everything will go right. But we're very excited that we have started our new experiments with an upgraded machine. We just started that at the beginning of August, and I hope we'll go back to experiments as soon as tomorrow. We've started these experiments. We were a little slowed down by flooding last week, but our lab is safe and we're going to go back to work.
Oh, shoot.
Do you think the Big Bang proponents are circling the wagons because of conflicts with creationism?
Are circling the wagons because of what?
It conflicts with creationism.
I don't know. I don't think that it's all religious. You know, obviously, some of it is. I mean, I briefly met with Alan Sandage, and Sandage was quite open that his studies of the Big Bang were partially motivated by his Christian religion. And obviously this was the case with Lemaitre, who originated with the Big Bang theory. There's lots of books that you can see on the bookshelves that relate religion to the Big Bang theory, and for that matter, to quantum mechanics. It's more bureaucratic, I think. I mean, the fact of the matter is people have invested a lot of taxpayer money in these theories. Now, the observations that have resulted, those are great observations. They can be used to support or attack the theory. But the fact that this is the paradigm that people have built careers on, have funded institutions on, this causes them to be more and more defensive. So we do, and I checked with my colleagues, it's just not my impression. It is more difficult today than it was 20 years ago to publish overall critiques of the Big Bang. In fact, it seems right now it's impossible, despite the fact that the past 20 years have seen an enormous increase in the published recognition of the contradictions in all of these 16 data sets. So the ability to publish contradictory data and contradictory conclusions has actually increased, but the ability to draw paradigm conclusions has decreased. How that's going to change is difficult to foresee, but I do see two possible trends that will change it. One is what happened in the fairy tale. Of course, once the kid said that the emperor is naked, everybody started laughing, and they saw that everybody saw the emperor was naked. So you can have a sort of piling on effect in which this orthodoxy becomes ludicrous. I did notice that Dr. Hassenfelder, who has a very high profile on the internet, she just said there has to be some shift in the overall cosmological paradigm. The other possible tendency comes out of fusion research. If fusion research reaches the point where we can see that using these plasma physics principles produce results like net energy, then it's going to really sharpen the focus on what does plasma physics imply for cosmology. Hard to say how long this will take. The editor of Nature magazine, he had a bad prediction too. He predicted in 1990 in print that the Big Bang would not survive the decade. So his prediction is already 20 years too optimistic. It's hard to say how soon the crisis in cosmology will reach its next stage. We'll see.
Thank you. Rodney, if you want to unmute and ask your question, I see you got your hand raised. If not, type your question in the chat box.
Yeah, I have a few questions, but I'll just ask one question right now.
Thank you.
The question I have is regarding the fuel for the device,
Right.
which is the boron mixed with or combined with hydrogen. So how do you get, I mean, I don't understand the process. How do you combine hydrogen with boron? How do you get the hydrogen? I don't understand.
Okay. Well, hydrogen is an abundant element. It of course, is the component of water. So you can get the hydrogen simply by passing a small amount of electricity through water.
Oh, okay.
Boron at the moment is mined from the ground. If we converted the entire world energy system to hydrogen boron fuel, we would only have to increase boron mining by 10%. So at the moment, the abundance of boron is not very relevant. If we needed more boron, boron is also a main constituent of sea salt. It has to be removed actually to use seawater, desalinated seawater for agriculture. So these are abundant elements. What happens is if these abundant elements are brought together at very high temperatures we have achieved in our lab, which are more than 2 billion degrees, 200 times the center of the sun, their electrical repulsion is overcome and they merge. They fuse together by their nuclear forces, which are active only over very short distances. But what they form for a very brief, a trillionth of a second, is what's called an excited state of carbon. So the carbon nucleus, which has 6 protons and 6 neutrons, is formed from the boron 11 and the proton, but it has too much energy to stay together. It's like a water droplet that's vibrating. It breaks apart almost instantly. And it breaks apart into 3 helium nuclei. So the net result is a process in which you put in hydrogen proton, a boron nucleus, and you get 3 charged helium and no neutrons. So that's important because neutrons are quite destructive. These helium nuclei have kinetic energy that they carry away the energy produced because the helium nuclei put together have slightly less mass than the proton and the boron. So by E equals mc squared, you have the liberation of a tremendous amount of energy. And this is the densest form of energy known at present. So this is 1,000,000 times more energy per unit mass than petroleum. So that's what we would be doing. And we haven't tested the device yet with hydrogen boron fuel, but we hope, all things going right, to get to those tests by approximately the end of this year. The reaction itself has been tested experimentally many times. You get these reactions through accelerators, and our colleagues in Prague actually derived these hydrogen boron reactions from a concentrated laser beam. And that's another approach people are using to use this fuel for fusion.
Okay. Just one other question. As far as the device itself, your focus fusion device, do you know if it will, or do you think it will require maintenance of any type, or is it just, I don't remember seeing anything about that.
Yes, well, all machines require maintenance.
Uh-huh.
Right now, we're in the scientific research stage. That's what we're going to be in up until the point we prove in the laboratory this machine can produce more energy out than we put into it.
Mm-hmm.
Then we'll move to an engineering stage to produce something that can roll down an assembly line, because this machine is, you wouldn't be building these generators, you'd be making them in a factory, like cars.
Mm-hmm.
That engineering stage, the most serious challenge is cooling the device. These electrodes are very small, so they really fit in your hand.
Mm-hmm.
And like all machines, some of the energy is going to be converted into heat.
Uh-huh.
So for a 5 megawatt electric generator, you have to take off approximately 2 megawatts of heat from this little anode. We think we can do that with compressed helium, but it will be very challenging. In addition, the anode's being bombarded by the plasma, so it's slowly eroding. Our goal is to have the anode last approximately 500 million shots. And this will be at about 200 hertz, which is about the same rate as your car fires its pistons.
Mm-hmm.
So if it lasts about a month before it has to be replaced, that should give us really good maintenance. Maybe it would have to be down 1 day a month. If it has to be replaced by a human being, there is some residual, very short-lived radioactivity with a half-life of 20 minutes that will have to be decayed out of the device.
Mm-hmm.
So it has to shut down for about 9 hours. It might be done robotically. We might have a little robot that replaces the anode, puts another robot anode in which case you might have a shutdown for only an hour per month. So realistically, we do expect that since the fuel will have negligible cost, the capital cost of these devices will be more than an order of magnitude less than the capital cost of electricity generation today. Labor may be your main cost. It may be how much you can reduce maintenance is what reduces the cost of electricity. But even with relatively conservative estimates of labor costs, we think that this device would produce electricity that is 10 times cheaper than any electric energy source today. So we would really be drastically reducing the overall cost of energy to the society.
Mm-hmm. Well, it sounds doable.
Well, visit our website, and I invite everybody to visit our website, which is LPPFusion.com. So it's easy to remember. And there's a lot of information, both on fusion and on Cosmology on the website. Pretty soon, if people are impressed with our technology, you'll actually be able to help us, because periodically, we just concluded one, we have crowdfunding campaigns on WeFunder where ordinary individuals can actually invest in this technology, buy shares in our company. So we just raised $700,000 that way. We hope next time to raise a good deal more. And if you want to be on our newsletter, just contact us through the website and we'll put you on the newsletter, which comes out roughly 6 or 8 times a year.
Okay, we had another question. Let's see. Is it observable that star formation is going up?
Is it observable that star formation is what?
Increasing, or can we see that there's more and more stars being produced, or is there not enough data to tell us that?
Well, at the moment, I would say the data is no, there are not more stars being produced. What you see in this diagram of increasing energy flows is that at each stage of evolution, you have an increase in the energy flows, but each stage is self-limited. In other words, if we look at the formation, for example, of a star like our sun, our star, our sun, is moving away from equilibrium in its evolution. So it's slowly heating up and energy flows are slowly increasing. Now, life has adapted to this over the 4 billion years that life has been on Earth, but that's going to be increasing. Because the sun is not animate, each individual blip of increased energy flow is self-limited. Stars are transient phenomena, we would say in plasma, or metastable. Now, it may sound funny to talk about something that's going to last 10 billion years as transient, but you have to take it in terms of its own scale. So if you take the time scale as the sun, as the total amount of time to replace the energy that it contains, the heat energy, the sun will replace its heat energy only about 1,000 times during its lifetime. If you take one of these plasmoids that form, whether the plasmoid is on the scale of a quasar, gigantic plasmoids, or it's our little plasmoids that last 30 nanoseconds, what you can find is the plasmoids last about 1,000 times the time it takes energy to cross them. So all of these plasma phenomena, inanimate phenomena, are transient phenomena. So they go up and then they go down. If you take them as a whole, there's a tendency for energy to increase. If you look at the universe as a whole, it entered a stage of thermonuclear evolution, the existence of stars, hundreds of billions of years ago. If we take a universe that's not a Big Bang universe. There was a peak in this development, which we see at a redshift of between 2 and 3. So that would be around 30 billion years ago. The universe was clearly brighter. For the development of life, that might have been a downside because it meant many, many more supernova, much closer to any planet that might have been developing life. If you look at our own galaxy, it was a lot brighter 5 billion years ago, or 8 billion years ago than it is now. So right now you have actually a descent in that inanimate phase of increase in energy density. Here on Earth, you have a different story. The development of life meant that the form of evolution itself has changed. With life, you have a continuous process in which the rate of energy flows has increased on average over time in a continuous sequence. So we are obviously descendant from the earliest forms of life, and the energy flows in the biosphere over that 4 billion period have increased by orders of magnitude. And that's indicated, for example, in the ratio of oxygen to carbon dioxide. In an equilibrium atmosphere, there should be millions or billions of times more carbon dioxide than oxygen. It's very reactive. Our present atmosphere has thousands of times more oxygen than carbon dioxide, only because of the evolution of life. And of course, if you look at human society as the latest phase in the evolution of life, we've enormously sped up the process of increasing the rate of energy flows. So here on Earth, which is the only planet we can observe life at the moment, the increase, the motion away from equilibrium has been continuous. In the inanimate pre-biological evolution, it was transient, up and down, up and down, up and down, within an overall tendency. So to get back to your question, no, star formation actually is slowing down both in our galaxy and in the universe as a whole. That was probably good for the evolution of life because we didn't have too many nearby supernovas to wipe us out.
Thank you. Question, any concerns about the ocean filling up with plastics, microplastics, since the source of your fuel is the ocean?
Well, if you watch some of our videos that are available on our YouTube channel, one of the great benefits of reducing the cost of energy is it makes possible 100% recycling. So there's an existing technology called the plasma torch. Westinghouse and other companies have developed this. And what happens in a plasma torch is you have a great deal of electricity flowing through matter, heating it to very high temperatures. And you have a magnetic field which rotates this matter so it separates elements according to their mass. So if you put garbage in, anything in, absolutely anything, this will absolutely reduce it to its constituent elements, and the elements will be separated and you can use them. So you smash up a car and put a car in there, you'll get out iron, copper, aluminum, and so on. If you put plastics in there, you'll of course get out basically carbon, oxygen, hydrogen. So right now, this technology is only used in certain high priority areas. Like it's used by the military to dispose of toxic chemicals, which they shouldn't be producing in the first place. If you reduce the cost of electricity tenfold, we could basically use it for anything. We could put all the plastics in there and we'd be getting out, carbon, oxygen, nitrogen, and so on. So certainly the garbage that fossil fuel economy produces is an enormous threat to the health of the entire biosphere. But we can shut that process down by moving to fusion.
Okay, how does entropy fit into your theory of cosmology?
Oh, I was hoping somebody would ask that. So the problem is that the second law of thermodynamics is not very well understood by most physicists, even though it has the understanding of science as a whole has really evolved. In its original form, what did the second law of thermodynamics say? It said that for a system close to equilibrium, where you could define a temperature, and temperatures can only be defined scientifically for systems close to equilibrium, that system would move closer to equilibrium. And you could define entropy for that system in such a way that all systems in that model move towards equilibrium. So that was in the 19th century. And even in the 19th century, people scratched their heads and said, well, gee, that seems to be a contradiction to the phenomena of life. Life seems to move away from equilibrium. If a living thing moves towards equilibrium, we call it dead. So this became an ongoing mystery. And steps to resolve this mystery started to be taken in the 60s of the 20th century with the work of Ilya Prigogine. And Prigogine studied systems far from equilibrium, where at temperature, which requires a Maxwellian distribution, cannot be defined. And basically what he discovered is the useful definition of the second law of thermodynamics is time is irreversible. Entropy can be defined mathematically for systems far from equilibrium, only specific to a given system. There's not an overall definition of entropy for any system. And it has to be defined in such a way as for that system, entropy always increases with time. So you can always define entropy, but the definition of entropy depends on the system. And it's very clear, for example, if you take a system as simple as a gravitating mass, it's clear that entropy does not lead that mass to go closer to equilibrium, because a large enough mass does tend to break up into smaller units. And especially when you take into account electromagnetism, a plasma with currents flowing through it tends to move away from equilibrium. So, and this is straightforward electromagnetism. The currents become greater, the energy flows become greater up to a certain point. So once you define entropy correctly for a given system, then you can see, okay, this system has to move either, depending on how far it is from equilibrium originally, either away from equilibrium or towards equilibrium. In the case of non-living systems, the motion away from equilibrium is always transient. It's delimited by some amount of time. It may be a time quite long compared with the time energy needs to cross that object. With living systems, we know that the system can move indefinitely away from equilibrium. And that's what we've seen in the 4 billion years that life has existed here on Earth. So it's not that you can't define entropy for a system, but the entropy has to be defined in terms of a given system. And it can't be, for example, the definition of entropy, for example, Shannon entropy, where you simply say, well, it's more probable for the distribution of matter to be even. That can be used for certain systems that are very close to equilibrium, but it can't be used in the general case. So a good book on the subject, by the way, is by Ilya Prigogine, and it's called Order Out of Chaos. And it's written for a popular audience and should be available on, I'm sure it's available on the net. So the funny thing is, Ilya Prigogine won the Nobel Prize in chemistry for his research on thermodynamics, and yet he, like Alfvén, who was also a Nobel laureate, he remained sort of a maverick in the field or a heretic in the field. And I would guess, I didn't take a poll, that the majority of chemists, the majority of physicists are not aware of his research into thermodynamics, which has developed into a whole big field of non-equilibrium thermodynamics, and are not aware that the whole paradoxes of the heat death of the universe and all that have long since been overcome, basically in the past half century.
Well, thank you for the final lecture. Generally, we will hopefully be able to get you off a gift certificate, gift card. That's usually take you out to dinner after a lecture or after a meeting, but since we're all virtual now, we will send you virtual money.
Well, I'll have to visit you and take you up on your offer. But before we go, I just want to say that I'll make this as a request, but I'm sure you'll accede to it, is I will be sending some of the scientific references that I've alluded to in this lecture, and you guys can post them in the comments, the description, when you post this as a YouTube. So people interested in, following up in the published literature, you'll be able to. And thanks very much for the invitation and for organizing this. How many people did we have?
We are recording, and if all goes well, I'll have the recording posted to our HAL 5 website. And if you want a copy, you can pull it down from here. I guess Tim, you're still on. Do you have anything for?
I'm still here.
Yep. Go ahead, and do you have anything you want to add to the meeting tonight?
No, that's about it.
Okay, well, thanks and good night.
Well, good night.